The standard model of particle physics offers an incredibly precise description of subatomic interactions, yet that precision requires maintenance. To make the mathematics of the standard model align with physical reality, physicists must manually input dozens of empirically fitted parameters. Mass is the most prominent example of this mathematical patchwork. Within quantum field theory, mass does not emerge naturally from the equations. It is inserted via 13 arbitrary Yukawa couplings and chiral phase conventions, forcing the math to match observed particle weights. The spacetime occupancy, or STO framework, discards the assumption that mass is a physical object. In this model, mass is not an intrinsic property of a particle. Instead, STO defines mass as an emergent topological phenomenon. It is a harmonic amplitude of resistance. When energy flows through the continuous geometry of space and time, it encounters localized curves. The resistance to that linear flow is what our instruments measure as mass. Treating mass as a fundamental building block requires retrofitting the math with ad hoc dials. If we analyze the physical structure of reality through continuous geometry, those arbitrary dials become unnecessary. At its most fundamental level, we find that the universe operates using a single continuous control dial, the measure of angular curvature over time. We can visualize this through a semicircular dial arcing between physical regimes. Adjusting a single continuous variable, the angle of the knob, triggers a transition across qualitatively different states of reality. The blue segment represents the background continuity of the universe. The curvature field is present everywhere, but in this state, no new energy is injected. Flow is uninterrupted, and no inertia registers. Crossing specific inflection points accesses a confined, compressed reservoir of energy. The medium hasn't changed, but the geometry of how the system accesses that energy has. Space-time uses one variable, curvature, to trigger the full spectrum of physical phenomena, from the emergence of the mass gap to the threshold of stellar ignition. In quantum field theory, the Majorana equation generates mass mathematically by coupling left and right-handed fields, utilizing an arbitrary right-handed spin-or phase factor. The STO mass operator replaces arbitrary phase factors with a geometric threshold scalar based on curvature, temperature, and time. The electron is the base mode of curved resistance. The muon and tau are denser angular modes, trapping more energy, while neutrinos are phase leakage. The lepton family forms a predictable spectrum of time-periodic thresholds, manifesting as resistance within a single underlying field. To understand exactly when this resistance forms, STO introduces the thermal angular symmetry law, or TASL. This law provides a direct mathematical link between thermodynamics and geometry. Under TASL, thermal gradients are re-expressed as angular derivatives in spacetime curvature. Temperature becomes a measure of curvature compression. This leads to a specific boundary condition known as the mass fingerprint and Avogadro threshold, MFAT. This operator identifies the exact density required for energy to transition into mass. When a 1-second temporal band at 66.6 Kelvin reaches an occupancy of exactly Avogadro's number, the field reaches a saturation point. This density creates a structural lock in the field, where the flow loses freedom and acquires the property of inertia. Avogadro's number defines the strict informational occupancy threshold where curvature flow reaches maximal packing density. This saturation converts informational density into measurable mass. Zooming out from quantum mass to the macroscopic nucleus, physicists calculate binding energy using the semi-empirical mass formula, treating the nucleus like a liquid drop. The formula is highly effective at describing observation, but it relies on an empirical asymmetry penalty to account for imbalances between protons and neutrons, offering no first principles explanation for why it exists. The STO framework replaces this fitted asymmetry parameter entirely with a strict geometric structure, the 24-cell dual lattice. In this 24-cell spatial lattice, protons are restricted to occupying the inner sheet, establishing a normalized radius of 1. Neutrons are consequently pushed to occupy the dual outer sheet, sitting at a strict geometric radius of the square root of 2. The empirical penalty observed in neutron-rich isotopes is a direct result of this radial gap. The strong nuclear force is governed by pure geometric sphere packing rules, operating without the need for tunable equations. Testing this geometric model against physical data immediately presents an empirical crisis. The static geometric limit of the square root of 2 predicts a neutron skin thickness of 0.89 femtometers for lead-208. The PREX-2 accelerator experiment measured the neutron skin of lead-208 at roughly 0.28 femtometers. On the surface, this discrepancy appears to invalidate the geometric model entirely. However, the nucleus is not a static crystal. To explain the discrepancy between a static geometrical lattice and a dynamic observation, STO applies the tetrahedral time dilation law. Consider a 3D regular tetrahedron. Projecting a static perpendicular height against a dynamic in-plane measure creates an invariant dilation lens of the square root of 3/2. Dividing the static lattice limit by this dilation lens yields the true observable expansion factor, 1.1547. Applying this 1.1547 projection factor to the excess neutrons in lead-208 yields a predicted physical skin thickness of exactly 0.311 femtometers. This 0.311 femtometer prediction lands perfectly within the PREX-2 experimental error band. The mathematical gap acts as a precise, predictable signature of the time dilation inherent to the geometry. These exact geometric rules scale far beyond the mass of particles and nuclei. They govern the emergence of light and color itself. When thick, rigid plastic is bent, a distinct whitening appears along the crease. The polymer chains are forced out of their ordered alignment, creating localized strain fields that emit energy. This is a macroscopic, low-energy instance of the universal deformation response principle. Mapping this to the quantum scale, a quark gluon plasma behaves identically. It emits spectral luminance purely in response to angular curvature stress within the confinement field. Light is a quantized curvature leak. It is the spatial symptom of thermodynamic deformation discharging into the surrounding geometry. If STO accurately describes the quantum thermodynamics of mass and light, it must also scale up to derive the ultimate cosmic metric, Einstein's general relativity. The STO framework executes a holographic derivation of gravity. The process begins with the basic local Clausius relation, which connects heat, temperature, and entropy. Starting with the Clausius relation, we substitute standard variables with STO operators. Temperature becomes the Tassel curvature temperature. Entropy becomes the ATCS surface ledger. Matching these constants resolves the algebra directly into Einstein's field equations without any outside coefficients. STO succeeds where others fail by recovering general relativity entirely from first principle thermodynamic curvature. It seamlessly unites the quantum information of a subatomic field with the cosmic gravity of a galaxy. A theoretical framework is only useful if it can be proven wrong. The STO framework provides strict, falsifiable discriminators. It mandates exact physical lab protocols, such as verifying the time dilation invariant ratio using high-precision pendulum gate tests. It requires astrophysical observation, mapping the hydrogen spectral ladder to confirm the exact placement of the 66.6 Kelvin mass gap band. A failure to align with any of these precise geometric bounds completely invalidates the entire STO framework. In the STO framework, geometry renders the metric of reality. Mass, energy, and gravity emerge as thermodynamic projections of time, completing a single cycle.